Hello, I'm Erin Bermudo from the Senior High School Department of De La Salle University, Manila, and on behalf of my co-authors, I present to you our research developing an assistive device for the visually impaired using ultrasonic sensors for distance and solidity determination. Visual impairment is prevalent worldwide and in the Philippines. It poses difficulty to the affected, especially in terms of navigation. Hence, assistive devices such as the walking stick were developed. However, this can only detect obstacles that are within its reach. Because of this, we have designed an ultrasonic space assistive device that provides the user distance and solidity information. Distance is given by calculating for the time of flight, which is done by multiplying the time it takes for the wave to return, and the speed of sound, which is 343 meters per second at 25 degrees on sea level, and dividing it by 2. On the other hand, the amplitude of the echo is determined by the ratio of the impedance mismatch of the object and the medium in which the waves are transmitted, which is, in our case, air. Acoustic impedance is given by Young's modulus, since the elasticity of a solid object affects the speed of sound passing through it. Young's modulus measures how stiff or dense an object is. Therefore, a denser material has a greater impedance mismatch to air. For instance, gold has a Young modulus of 78 gigapascal, whilst human skin ranges between 5 kilopascal and 140 megapascal, according to Cholera and colleagues in 2016. The strength of reflection at a given distance can be a representation of the hardness of the material surface. Given the knowledge of how far a surface is, using traditional time-of-flight measurements, and being able to measure the strength of the echo, an estimate of the material's density can be determined. In order to build our prototype, the components were attached to a regular walking stick. In our lab experiments, the raw echo amplitude with the ultrasonic sensor pointed at a person at a distance of 25 centimeters was only approximately 26 millivolts. Hence, we implemented amplification, peak filtering, and envelope generation in our design so that the Arduino could digitize the return echo properly. Our design implemented an acoustic feedback system using 2 piezoelectric buzzers. Buzzer A, which is for distance measurement, would produce sound at a higher rate as a sensor nears an object, similar to a car parking. Buzzer B, on the other hand, is for solidity determination, wherein at a specific distance will sound off determining how solid the object is through various sound frequencies. These components were placed in a box attached to the end of the stick. The system is then powered by a power bank that is attached near the handle of the stick. The experiment was adapted from Lee and colleagues' study in 2014. We gathered 16 participants and splitted them into walking stick users and prototype users. Prior to the experiment, they were briefed on how to use and operate their respective devices. Each participant was given about 3 minutes to try their device around the amphitheater inside the campus with a blindfold on. They were also shown the route but were disoriented before their turn. During the experiment, 3 researchers supervised and a post-interview was conducted. Here is an image of the whole route. Present in this course are varying elevations, cement pavement with rough finishes, lampposts, plants, stairs, and hallways. From the table, prototype users had a lower collision frequency than walking stick users. This could mean that the prototype was more effective in detecting objects, especially those that are smaller and harder to sense, like small plant pots. Besides this, data shows that prototype users also have a faster course completion time by roughly 36 seconds. To conclude, this research was conducted to design an ultrasonic space assistive device that would increase the degree of independence of the visually impaired. Based on the results from sensor characterization, there is a direct relationship between the hardness of a material and its wave amplitude. The participants underwent an indoor-outdoor course, and as we have seen from the results, the prototype users had a faster course completion time and lower collision frequency as compared to the walking stick users. With this, we can conclude that the prototype was able to give the users sufficient information on their surroundings. It was able to notify them ahead of time on the obstacles along their path, and likewise, reroute them and avoid these obstructions. Here are recommendations for future research. We do suggest gathering more test subjects in order to be more statistically accurate. We also recommend a more extensive experiment on the prototype in a variety of indoor and outdoor environments. Doing this may help find out the other limitations of the device and further improve the interface. Based on the post-interview, the ergonomics of the device should be considered since the test subjects found the prototype uncomfortable to use. According to them, the device was quite heavy and the grip could be further improved. Moreover, using a different sensor, particularly sensors that have a wider and longer range of detection, is recommended. So, this concludes our presentation. Thank you for watching and stay safe, everyone.